Hello everyone. I'm B. Sankaralakshmi, working as an assistant professor at the Department of Artificial Intelligence and Data Science in Ramco Institute of Technology, Rajapalam. In this video, we are going to learn tree traversals. Shall we enter into this video? Yes, we shall. First, let us have an introduction to trees. We are going to do tree traversal on binary tree. So first we should, before doing tree traversal, we should know what is meant by a tree ADT. Here is the definition. I read out the definition, you just follow me. A tree is a non-linear data structure. A tree structure is a way of representing one or more nodes in a hierarchical manner in which one node is designated as the root of the tree and all the remaining nodes can be partitioned into non-empty sets, each of which is a subtree of the root. From this definition, we know that a tree is a collection of one or more nodes, and all those nodes are arranged in a hierarchical manner in which only one node will be acting as the root of the tree. And all the remaining nodes are said to be children nodes. And these children nodes can be divided into number of subtrees. The following diagram shows the structure of a tree ADT. If you look at this diagram, you can come to know that capital A is the root of the tree and all the remaining nodes are said to be the children of the root node. And these nodes are divided into number of subtrees. If you take this particular part, this is left subtree of the root and this is right subtree of the root and this is what middle subtree. Next, we are going to see some of the basic terms used in tree ADT. Let us see one by one. We are going to start with root node. The root node of the tree is the node with no parent or the topmost node in the tree. There can be at most one root node in a tree. Example, A is the root of the given picture. If the root node is equal to null, then it means that the given tree is an empty tree. Therefore, root node is nothing but a node with no parent or otherwise the topmost node of the tree. And here in this diagram, root of the tree is capital A because it doesn't have any parent to it. And this is the topmost node in the tree. Next term is edge. An edge refers to a link from parent to child. Each parent is connected with their children through links. Again, come to this picture. Here, each pair of nodes are connected with the help of links or edges. Okay, I take this particular pair A and B. These two nodes are directly connected through an edge. Therefore, if you take an edge in the tree structure, it represents that the connected nodes are having parent-child relationship. Next term is leaf node. A leaf node is a node with no children, right? Therefore, a node with no children is called a leaf node. The other names of leaf node are terminal node or external node. Example, in our picture, the leaf nodes are E, J, K, H, I. These are leaf nodes because they don't have any children to it. Next term is siblings. Children of the same parent node are called siblings. Example, in our picture, B, C, D are the sibling nodes. Similarly, E and F and H and I are the siblings. If you take B, C, D, these three nodes have the same parent, that is capital A. Similarly, if you come to the pair E and F, these two nodes also have the same parent, capital B. And H and I have the same parent, capital D. Therefore, these pair of nodes are said to be siblings. Next term is path. A sequence of consecutive edges is called a path. Example, a path from the root node A to node I is given as ADI. A path in a tree structure is nothing but a consecutive edges, sequence of consecutive edges, right? Therefore, here I take the path from root node A to I. And on this path, we have totally 3 nodes, including the node I. And if you count the number of edges on this path, we have only 2 edges. The first edge connects A and D, and the second edge connects D and I. Therefore, we can represent the path of node I as ADI, or the number of edges equal to 2. Next term is ancestor of a node. Any predecessor nodes on the path from the root node to that particular node are called ancestors of that node. Example, A, C, G are the ancestors of node K. The root node doesn't have any ancestors. Ancestor nodes are nothing but the predecessor nodes on the given path. Suppose I want to determine ancestor nodes of K, right? Therefore, I have to choose the path from the root node to that particular node in order to determine the ancestor nodes of K. And on this path, we have totally 4 nodes, A, C, G, and K, right? But we are actually calculating or determining ancestor nodes of K only. Therefore, we have to exclude K. Hence, in this path, we have other 3 nodes, A, C, G. Therefore, the ancestor nodes of K are A, C, G, or otherwise, the predecessor nodes on this path are A, C, G. Next term is descendant of a node. A descendant of a node is any successor node on any path from that node to a leaf node. Example, C, G, K are the descendant nodes of node A. Leaf nodes don't have any descendants. In the previous definition, ancestor of a node, we have taken a path from the root node to that particular node to which we determine ancestor nodes, right? But in case of determining descendants of a node, we have to choose the path from that particular node, that is, to which we determine descendant nodes to the deepest leaf node, right? And here, if you take any particular leaf node, it doesn't have any descendant nodes, okay? In case of ancestor of a node, the root node doesn't have any ancestors. Again, you just come to the picture. And here, C, G, K are the descendants of the root node, right? That is, we are going to determine the descendant nodes of the root node, right? And in order to determine the descendants of this particular node, we have to choose the path from that node to the deepest leaf node. And here deepest leaf node are J and K. So I take this path. We can choose either of these two paths. I take this one, A to K. Therefore, here the descendant nodes of A are the successor nodes, that is C, G, K. Next term is parent node. An immediate predecessor of a node is called the parent node of that node. Example, B is the parent of E and G. We have already seen what is predecessor node on a particular path and what is successor node on a particular path, right? Therefore, here parent node is defined as an immediate predecessor of a node. If you take any particular path, let us take B, right? Let us take this particular path. Okay. And here B is the parent of E and F, right? If you take E node or F node, the immediate predecessor of these two nodes is capital B, which is the parent of these two nodes, right? This is what the definition of parent node. Next one, child node. An immediate successor of a node is called the child node of that node. Example, E and F are the children of B. Successor node in a sense, if we choose any particular path in the given tree structure, then suppose I want to determine the children nodes of B, right? And in such case, I have to concentrate on the successor nodes of that particular path. And immediate successor nodes of B are E as well as F. Therefore, these two nodes are said to be children nodes of B. Next term is level of a node. Every node in the tree is assigned a level number in such a way that the root node is at level 0. Children of the root node are at level 1. Thus, every node is at one level higher than its parent level. So, all child nodes have a level number given by parent's level number plus 1. Example, level of node B is 1 and level of nodes E and F is 2. In case of tree structure, the level number usually starts from 0. If you take root of the tree, we can say that it is at level 0. And if you come to next level, it is level 1. And next one is level 2. And the last level of this tree structure is level 3. Okay. And here we are going to determine the level of node B, right? And here level of node B is 1. How do we calculate level of a particular node? In order to determine or know the level of a particular node, we should know the level number of its parent. Here we have already seen that the level number of root node is 0. Therefore, how can we calculate the level number of node B? Just parent's level number plus 1, right? Just by following this formula, we can find out the level number of node B. And its parent node's level number is 0. Therefore, 0 plus 1 is equal to 1. Level of node B is 1. Come to the next level, E and F. If you want to calculate the level number of these two nodes, then we should know the level number of B, right? We have already calculated the level number of B, which is 1. Hence, the level number of E and F is 1 plus 1 is equal to 2. That's all about level of a node. Next term is depth of a node. The depth of a node n is given as the length of the path from the root node to that particular node, that is n. The depth of the root node is 0. Example, the depth of the node I is 2. We can calculate depth of each and every node in the given tree structure. If you take the root node, the depth is 0. Okay. How can we calculate depth of a node here? In order to determine depth of a particular node, we have to choose the path from the root node to that particular node. Okay. And here what is given? We have to determine the length of the path. We have already seen what is path. A path is nothing but a sequence of edges, right? So here I'm going to determine the depth of node I. Again, I choose the same path which is chosen in the example of path, right? So here the depth of node I is said to be 2. If you count the number of edges here, 2, right? Therefore, length of the path is 2. Next, come to the next term. Internal node. A node with at least one child is called an internal node. We have already seen what is an external node, right? An external node is nothing but a leaf node, which doesn't have any children to it. Therefore, internal node is a node with at least one child, right? Here, example is A, B, C, D, F, G are the internal nodes of the given tree structure. Leaf nodes are here E, J, K, H, I. And all the remaining nodes are said to be internal nodes of the tree. That is A, B, C, D, E, F, G, and that's all. These are the internal nodes, right? Next term is height of a tree. Height of a tree as well as height of a node are the most important terms used in the tree ADT. Let us see the first one. How do we calculate height of a tree? The height of a tree is the total number of nodes on the path from the root node to the deepest leaf node in the tree. A tree with only a root node has a height of 1. Example, height of the previous diagram tree structure is 4. Here, height of a tree can be calculated by choosing a path from the root node to the deepest leaf node. We have already seen what are the deepest leaf nodes here. That is J and F, right? Therefore, to determine or calculate the height of this tree structure, we have to choose the path from the root node to the deepest leaf node. Therefore, we can choose either of these two paths, right? Since J and K are the deepest leaf nodes, I choose this one, A to B, B to F, and F to J. Therefore, here we have to count the total number of nodes instead of edges, right? In case of path and depth, we have counted the total number of edges on the particular path. But in order to calculate the height of a tree, we have to count the number of nodes on the path. Okay. And on this path, we have 4 nodes, right? A, B, F, J. That is including the deepest leaf node. Therefore, height of the tree is 4. Next term is height of a node. We can also determine height of a particular node in the tree just as the height of a tree, right? And it is a total number of nodes on the path from the root node to that particular node. Example, height of node G is 3. In order to calculate height of any particular node, we have to choose the path from the root node to that particular node. And what example I have given in the slide? Height of node G. Therefore, I take node G in this diagram. Okay. And here, I have to choose the path from the root node to that particular node in order to know the height of this node, right? So I choose this path, A to C, C to G. And here we have totally 3 nodes on this path, A, C, G. Therefore, height of G is 3. Next term is degree of a node. Degree of a node is equal to the number of children that a node has. The degree of a leaf node is 0. Example, degree of node F is 1. Degree of a node can be calculated by counting the number of children that particular node has. Example, degree of node F is 1. Again, you come to this diagram. If you take the node F, it has only one children, that is left child J. Therefore, degree of F is 1. And if you take the root node, it has 3 children B, C, D. Therefore, degree of root node is 3. If you take any particular leaf node, we can say that degree of each and every leaf node is 0 because they don't have any children to them. Next term is subtree. Any node of the tree along with its descendant nodes is called a subtree. We have already seen what is a subtree in the beginning itself, that is in the definition of tree, right? Therefore, here subtree is nothing but any node of the tree along with its descendant nodes. That is what subtree. And in our example diagram, we have 3 subtrees for the root node, right? This is left subtree and this is right subtree. And this is what? Middle subtree. That's all about basic terminologies of tree ADT. Next coming diagram shows each and every term that we have seen earlier. In this tree structure, the root of the tree is capital A and the pair of nodes are directly connected with the help of edge. This is what an edge. And D node is the parent node, right? And I and J are children nodes. If you take a particular node along with its descendant nodes, then it is said to be a subtree. This is what a subtree here. And leaf nodes in this diagram are I, J, K, F, G, H. Sibling nodes, F, G, H. And if you come to level of each node, here root node is at level 0 and B, C are at level 1 and the next level is level 2 and the last level of the tree is level 3. Next, we are going to see types of trees. We can classify the tree ADTs into different categories. They are general tree, binary search tree. Apart from these three types, still we have some more special trees. They are AVL tree, red-black tree, and splay tree. And in this video, we are going to see about only binary tree because we are going to do traversal on binary tree alone. Okay. Next one is, what is a binary tree? Here is the description. A binary tree is a data structure which is a collection of elements called nodes. And in this structure, the topmost element is said to be the root of the node. The main property of a binary tree is each and every node is permitted to have either zero child or one child or at the most two children. Okay. If you take any particular node of a binary tree, it can have at least zero child or one child or at the most two children. A node that has zero children is known as a leaf node or a terminal node or an external node that we already know. Next one, each internal node has two pointers, left pointer as well as right pointer. Left pointer points to left child of the node and right pointer points to the right child of the node. The following diagram shows the structure of a binary tree. If you look at this diagram, here one is the root of the tree. And if you take any particular node in this tree, except the leaf node, each one have two children to it, right? If you take one, it has two children, 2 and 3. If you take 2, it also has two children, 4 and 5. If you take 3, it also has two children, 6 and 7. And here 4, 5, 6, 7 are the leaf nodes of this particular tree because they don't have any children nodes to them. Next one is types of binary trees. We can classify the binary trees into different categories based on the number of children that each node has. Let us see the first type, perfect binary tree. A binary tree is said to be a perfect binary tree only if each node has exactly two children and all leaf nodes are at the same level. The following diagram shows the structure of a binary tree, perfect binary tree, right? From the name itself, we can understand the structure of the perfect binary tree. Perfect in the sense, if you take any particular node in the binary tree, except the nodes at the last level, that is leaf nodes, each one must have two children to it. If you take 18, it has two children, 15 and 30. If you take 15, it has two children to it, 40 and 50. If you take 30, it also has two children, 100 and 40. Okay. And all the other nodes, that is 40, 50, 100 and 40 are at the same level. Therefore, they are said to be the leaf nodes. Next category is full binary tree. A binary tree is said to be a full binary tree only if each node has exactly two children or no children. In case of full binary tree, if you take any particular node, it must have either exactly two children or no children, that is zero child. And the following diagram shows the structure of a full binary tree. Okay. And here, the root node 1 has 2 children and 2 has 2 children. And here, the right child of root node, that is 7, has no children to it. And again, 4 has 2 children, right? Therefore, here the main constraint or the property to be satisfied is each and every node can have either exactly 2 children or no children. Next category is complete binary tree. A binary tree is said to be a complete binary tree only if it satisfies the following two properties. The first property is every level except the last one is completely filled. And the second property, all nodes appear as far left as possible. The following diagram shows the structure of a complete binary tree. And here, if you take each and every level of this tree except the last level, all the levels are completely filled. That is, in the first level, that is 0th level, there is only one node, root node. And if you come to the next level, here we have two nodes. And if you come to the last level, here we have only two nodes. Still, we can insert two more nodes into this level, right? Therefore, except the last level, all the remaining levels are completely filled. This is what first property given here. And the second one is, whenever we construct a complete binary tree, we should have to insert each and every node into it only from left to right. That is what the second property says. If you take the last level of this particular tree, we have the two nodes, that is as the leftmost nodes of the tree. Okay, only after completing the left side, we can come to the right side. Next type is, that's all about the types of binary tree. What are the types we have seen? Perfect binary tree, full binary tree, and complete binary tree. Now we have come to binary tree traversals. This is our main topic, right? Let us see what is traversal. Traversal is a process of visiting each node in the tree exactly once. Traversal in the sense visiting each and every node or accessing each and every node in the given tree structure in order to print them or in order to count the number of nodes in the tree. In case of data structures named array and linked list, we can have traversal on each element in a sequential manner. But in case of tree structure, it is not necessary that we should traverse the nodes in sequential manner. Okay, instead of that, we can traverse each and every node in different ways. And the ways differ in the order in which we are going to visit or traverse each node of the tree. Therefore, binary tree traversals can be classified into 4 different categories based on the order in which the nodes are traversed or visited. The types are pre-order traversal, in-order traversal, post-order traversal, and level order traversal. According to the order in which we are going to traverse each and every node of the tree, we can have 4 types of tree traversals, right? Let us see one by one in detail along with suitable example. The first type is pre-order traversal. To traverse a non-empty binary tree in pre-order, the steps to be followed are, there are 3 steps. The first one, visiting the root node, and the second one, traversing the left subtree, And the third one, traversing the right subtree. Here, the term non-empty binary tree in the sense the given binary tree is not an empty tree. That is, it consists of a number of nodes in it. And in order to traverse a non-empty binary tree in pre-order, we have to follow these three steps. That is, we have to start our traversal process only from the root node. So first we visit root node of the tree, and once we have completed visiting root node, next we can move on to left subtree, right? And once we have completed left subtree, we can go to right subtree. Okay, and with this right subtree, we can complete or finish our traversal process. And this pre-order traversal is also known as depth first traversal. If you take the term, if you take the term pre in the name pre-order, it refers to that the node is, that is the root node is accessed or visited prior to any other nodes in both left subtree as well as right subtree. And this pre-order traversal is mainly used to extract a prefix notation from an expression tree. If you are given an expression tree, you can easily extract prefix notation with the help of this pre-order traversal, right? In order to get prefix notation, you have to do pre-order traversal on the given expression tree. Let us have one example. Traverse the following binary tree in pre-order and print the elements. Now we are going to do pre-order traversal on this binary tree, right? The given binary tree is this one. And here root node is 1, 2, 3, children nodes, and leaf nodes are 4, 5, 6, right? Let us start our traversal process from the root node, because here the three steps to be followed are visiting the root node, traversing the left subtree, and traversing the right subtree. Okay. So in first step, we visit root node 1. Now root node is visited. Come to the second step. Once we have completed visiting the root node, next we have to move on to the left subtree of the root node. And left subtree is nothing but this particular portion, 2, 4, 5, right? So again, if you have come to left subtree of root node, again we have to focus on the three steps to be followed. What is given in the first step? Visiting the root node. And in this left subtree, the root node or parent node is 2. Therefore, we have to visit node 2 at first. Okay. So next visited node is 2. And in step 3 only, we go to left child of 2, that is 4. And only after completing the left child, we can go to the right child of the parent node 2, that is 5. Now we have completed the traversal on left subtree of the root node. Okay. Next we shall move to right subtree. And here in right subtree we have two nodes, 3 and 6. Again, you have to focus on the three steps. What is the first one? Visiting the root node, right? And here the root node or parent node is 3. Therefore, we have to visit 3 at first. And after visiting 3, we reach the last node, that is 6. Therefore, the resultant order is 1, 2, 4, 5, 3, 6. This is what the output of the pre-order traversal. Next one, in-order traversal. To traverse a non-empty binary tree in order, the steps to be followed are the first one, traversing the left subtree. Next one, visiting the root node. Next one, traversing the right subtree. Okay, so these are the three steps to be followed in order to perform in-order traversal on a given non-empty binary tree. And this in-order traversal is also known as symmetric traversal. The term in the name in order refers to the root node is accessed or visited in between the left and right subtrees, right? That is, the root node is actually visited in between, that is after visiting the left subtree and before visiting the right subtree. This in-order traversal is mainly used to extract an infix notation from an expression tree. If you are given an expression tree, you can just extract an infix notation of that expression just by doing in-order traversal on that particular tree. And next one is, it is also used to produce the elements of a binary search tree in an ascending order. If you do the same traversal, in-order traversal on a binary search tree, then you will get all the elements in ascending order or alphabetical order, depending upon the values of each node given in the tree structure. Next, we shall have one example. Traverse the following binary tree in order and print the elements. Again, I have taken the same binary tree structure in order to perform in order traversal. Okay. Here, what are the steps we have seen? First, we have to visit left subtree, and next we have to visit root node, and finally we can visit right subtree, right? Therefore, here left subtree is this portion because 1 is the root of the tree, right? So this is what left subtree. And once you have found the left subtree of the given tree, next you have to focus on the 3 steps. What is first one? Traversing left subtree. And here 2 is the parent node, just like the root node. Therefore, we have to start our traversal only from the leftmost child. And here leftmost child is 4, right? So the first visited node is 4. In the second step, we come to the root node or parent node. That is, after visiting the left child, we can just go to the parent node. Here parent node is 2. And after completing visiting parent node, we can go to right child. That is 5. Therefore, till step 3, we have visited nodes 4, 2, and 5. Come to step 4. Only after visiting or completing traversal on left subtree, we can go to root element of the tree. That is 1. In this step, 1 is visited. And the next step, after completing or finishing visiting the root node, next we shall go to right subtree. And here in right subtree, we have 2 nodes. Okay, again we have to start our traversal process on right subtree only from the leftmost child. Since the node 3 doesn't have any left child to it, we can directly visit the parent node here. Therefore, in this step, node 3 is visited. And after visiting node 3, we can come to node 6. And this is what the last node visited here. Therefore, the resultant order is 4, 2, 5, 1, 3, 6. This is what the output of in-order traversal on this binary tree. Next category is post-order traversal. From the concept of previous 2 traversals and from the name of this traversal, you can come to know that what are the steps to be followed, right? To traverse a non-empty binary tree in post-order, the steps to be followed are the first one, traversing the left subtree, traversing the right subtree, visiting the root node. In case of post-order traversal, first we have to start our traversal only from left subtree of the root. And next we have to continue our traversal on right subtree. And finally, we have to visit the root node. With this root node, the post-order traversal will be over. And the term post in the name post order refers to the root node is accessed or visited after the left and right subtrees. Okay. So in this case of traversal, we visit the root node at last. That is only after visiting left as well as right subtrees. And this traversal is used to extract a postfix notation from an expression tree. If you are given an expression tree, just by doing post-order traversal on the given tree, you can determine the postfix notation of that expression. Let us have one example to deeply understand post-order traversal. Traverse the following binary tree in post-order traversal and print the elements. Here also, I have taken the same tree structure in order to perform post-order traversal just for simplicity. Okay. And here the root node is 1. What are the steps we have seen? First, we have to visit left subtree. And after completing left subtree, we have to move on to right subtree. And only after completing right subtree, we can go to root node, right? Therefore, here come to left subtree. This portion is left subtree of the root, right? And here we have to start our traversal from leftmost node. That is, here parent node is 2 and left child of 2 is 4. Therefore, we start our traversal from 4. Now, 4 is visited in step 1. In step 2, we have to visit the right child. That is, the second step is traversing right subtree. Only after traversing right subtree, we can go to the parent node or root node, right? Therefore, here, after visiting 4, next we move to 5. And only after visiting 5, in step 3, we visit 2. At the end of step 3, we have visited 4, 5, 2. Come to step 4. Now we have completed traversal on left subtree. Next step is traversal on right subtree. So after completing left, we have to jump into right subtree. And here in right subtree, we have 2 nodes, 3 and 6. Again, we have to start our traversal process from leftmost child. Since the node 3 has no left child to it, we can move on to the right child directly. Okay. So in this step, 6 is visited. And after visiting 6, we come to 3. In step 5, 3 is visited. And now we have completed traversal on both left as well as right subtrees. So in step 6, we have come to root node. And finally, root node is also visited. Therefore, the resultant order is 4, 5, 2, 6, 3, 1. Right? This is what the output of post-order traversal on this particular tree. The last traversal type is level order traversal. The simplest type of traversal, right? Here, the nodes of a binary tree are traversed or accessed level by level. That is, we have to start our level order traversal only from the 0th level of the tree. That is from the root node. All the nodes at a level are accessed before going to the next level. Once you have completed the traversal on level 0, next you can go to level 1. And after completing level 1, you can go to level 2. Likewise, you can complete each and every level of the tree. And this traversal is also called as breadth first traversal. Let us have one example. Level order traversal example. Traverse the following binary tree in level order and print the elements. We already know that in case of breadth first traversal, we will use queue data structure. And in case of depth first traversal, we will use stack data structure. Okay. So the first step is given binary tree is this one, right? And here we are going to perform level order traversal. Let us start our traversal from the root node of the tree because it is at level 0, which is the first level of the tree, right? Therefore, in step 1, 5 is visited. That is, it has been enqueued into the data structure queue. Come to next step. After visiting level 0, that is root node, next we have to go to level 1. And in level 1, we have two nodes, 12 and 13. On level 2, we have three nodes. We have to complete each and every level in this tree, right? Now we have completed up to 5 and next one, 12 and 13. Okay. After completing 12 and 13, next we visit 7, 14, 2. 7, 14, 2. And in this step, we have completed up to level 2. Next, come to level 3. And here we have 6 nodes, 17, 23. And in step 6, we visit 27, 3. In step 7, we visit 8 and 11. We all know that the working principle or the philosophy of queue data structure is first in, first out or last in, last out. Therefore, the resultant order of level order traversal is 5, 12, 13, 7, 14, 2, 17, 23, 24, 27, 3, 8, 11. This is what the output of level order traversal, right? As we traverse each and every level or each and every node on a particular level in this tree, all the elements are enqueued into the data structure and each and every element is dequeued from the queue data structure when we move on to the next level, right? Therefore, this is what the output of this particular traversal. I hope you all have enjoyed this video and understood the tree traversals well. Thank you for spending your precious time on watching this video. Thank you once again.